Okay, so as we talked about when we talked about periodic trends, we know that as we go down the periodic table, atoms get bigger as we layer on those energy levels with the electrons. And as we go across the periodic table, our atoms get smaller because we have a greater nuclear charge without adding any additional electron energy levels. Well, now we're talking about the size of ions. And they follow the same trends, except we need to think about a couple more things. First off, cations are smaller than the atoms they came from because we are removing electrons. We're removing layers. So an example there would be that a sodium cation is smaller because it lost a whole energy level, right? It's gone down to that lower energy level, and so it's going to be smaller. Whereas an anion, like let's think about fluorine. If we have fluorine and we add another electron to fluorine, that electron that it wants to have that octet rule, then it's going to get bigger because it's going to have some electron-electron repulsion in that orbital there, right? You had one electron hanging out by itself, and now you've got two in that orbital, and so the other one's going to back up to give some room because of that repulsion. So that's why anions are larger. Across a row, ions do get smaller, and then there's suddenly an increase, and that's because the first half of a row is cations and the second half of the row are the anions. Let's take a look at a picture of this. Across the period, nuclear charge increases no matter what. And so that is going to slowly pull in those energy levels smaller and smaller and smaller as we look at our cations here. But then when we go from a cation with carbon, the next guy, nitrogen, is definitely an anion. He would rather gain electrons than lose them. Huge increase there because we are gaining, filling that energy level with all those electrons, and so we have that electron-electron repulsion. And these guys, keep in mind, they all have the same number of electrons, whether it's the nitrogen -3 anion, the oxygen -2 anion, or the fluorine -1 anion. They all have the same number of electrons and the same amount of shielding and the same energy levels. But the reason that fluorine is smaller than oxygen and oxygen is smaller than nitrogen is because of that greater nuclear charge. We're increasing the number of protons in the nucleus. So this same effect going on here that we have going on here. So an isoelectronic ion is an ion containing the same number of electrons. So as we said before, these guys and neon and sodium cation and the magnesium cation, all of those guys, they all have 10 electrons. They all have the same electron configuration as we can see it right here. However, this is what they actually look like as far as their radius. So we've lined them up from the smallest to the biggest, and it is because of that proton-electron ratio. Positive ions have more protons, so they are smaller because those protons are pulling in on those electrons. Let's practice this now. I'd like you to take these guys and put them in order of decreasing size. So go ahead, press pause, and give that a try. So here we have them numbered. Keep in mind, I asked for decreasing. When my example, I showed increasing. So we're going to put them in the reverse order. So we're going to have our biggest one right here, our phosphorus. with the -3, and then sulfur -2. Argon is neutral, our noble gas there. And then we're rounding the corner into the next energy level with a calcium, I'm sorry, I jumped, a potassium +1, and then our calcium +2. And that is because calcium +2, even though it has the same number of electrons as these guys, has the most protons. So that's going to have the greatest effective nuclear charge there. And our phosphorus with the -3 has the least number of protons, so the lowest effective nuclear charge. But they all have the same electron configuration and the same number of electrons. Okay, so now let's bring these guys together. We've been talking about ions and about their sizes and the energy in the bonds. So let's make some ionic compounds. So first off, ionic compounds are solid crystals. That means we have a metal and a non-metal bonded together. And we'll talk about them also when we talk about acids and bases. All right, so let's bring these ions together into ionic compounds. We will form solid crystals. Ions align themselves to maximize attraction between the opposite charges to, of course, minimize repulsion between like ions. So they are going to line up so that positives are with negatives and negatives are with positives. And we will discuss this lattice energy. So an indication of how tightly an ionic crystal is held together is by its lattice energy. Again, if lattice energy is negative, it is exothermic from the point of the view of the system. How do we define system? System is the outside of this bond. So meaning if I'm holding a reaction in my hand is the system. So if that reaction is giving off heat, that reaction is exothermic and I am experiencing that heat. If I'm holding a melting ice cube, then that ice cube is absorbing heat from me and it is endothermic. So we have to be careful because when we look at a bond from the point of view of the bond is looking as it's giving off heat if it's exothermic. And if I'm holding something and it gets hot, I'm looking at it as I'm absorbing the heat, right? So we have to make sure that we're looking at it from a specific point of view. So the more negative the lattice energy is, then the stronger that bond is. So the solid crystals that are formed from ionic compounds coming together are very strong. And they are going to form this lattice work, which makes them even stronger. So let's take a look at the formula for lattice energy. I'm going to give you a minute to take a look at this. And what do you see there? Okay, so here we have the formula for lattice energy. What do you notice about it? That's right. It looks like Coulomb's law, doesn't it? We've got our constant here. We've got the charges of the ions divided by the radius, and that's going to tell us how much energy is there. That makes sense, right? Because we're talking about the energy in a lattice, and a lattice is really about the bonds between those ions. The lattice energy is more exothermic with more highly charged ions. So that makes sense. This number is going to get bigger. So the bigger the charges are, the bigger that number is going to be, the stronger and more exothermic that bonding is going to be also. So let's take a look at these guys. So out of the following pairs of compounds, pick the one with the more exothermic lattice energy. So I'm going to give you a minute to take a look at that. So go ahead and pause, and then we'll go over it. Okay, so if you're having a hard time, let's take a look at number 1 first. The first thing you're going to look at are those charges. So magnesium, we know very quickly, looking at the periodic table, is a +2. Oxygen's a -2. So when we put those together, we're going to end up with a -4. And that's a lame 4. And here, sodium's a +1, fluorine's a -1, so we're going to end up with a -1. Well, we already said the bigger the charge, the more exothermic, the stronger the lattice. So -4 is our winner over -1. Let's take a look at calcium fluoride and aluminum chloride. So calcium is a +2. Fluorine is a -1, so that's going to bring us to a -2 for those guys. And aluminum is a +3, and chlorine's a -1, so that's going to bring us to a -3. And so we see there that aluminum chloride is our winner. How about this last one? What do we got? Oh, I was a little sneaky with this one. Strontium is a +2 and iodine is a -1 for a -2, but sodium oxide is also a -2, so same charge. So now we need to take a look at that radius. And so when we look, we compare strontium and sodium on their size. Strontium is larger than sodium. And then when we compare iodine and oxygen, we see that iodine is also larger. So we know that strontium and iodine are going to have a larger radius than sodium and oxygen. Well, we're dividing by that radius, so we want a smaller number to have bigger energy, right? The closer together they are, the more energy they're going to have. The further apart they are, the less energy that they are going to have. So we see that sodium oxide is going to have a stronger lattice energy with a smaller radius to give us that bigger number right there. So that's where we are for that one. So we're going to stop here on our notes today, and I want you to check your Google Classroom for problems to do. Thanks, guys.